Hi, this video provides a brief walkthrough of a new paper that we just published in NeuroImage entitled Evaluating Dynamic Bivariate Correlations in Resting State fMRI, a comparison study and a new approach. This is joint work with Yuting Xu, Mary Beth Nobel, and Brian Caffell. So this paper deals with a kind of a hot topic, which is dynamic correlations in resting state fMRI. So to give a little background, in recent years there's been an increased interest in performing studies of brain connectivity. And these types of studies seek to describe how different brain regions interact with one another and how these interactions depend on experimental conditions and behavioral measures. Here's a simple example where we show that the ventromedial prefrontal cortex is correlated with these three other regions. It's typically been assumed that the connectivity between distinct brain regions is constant across times, at least within a certain experimental condition. So researchers have believed that the correlation between different brain regions is static across time. However, recently there's been an increased interest in quantifying possible dynamic changes in connectivity, particularly in the context of resting state fMRI. Here it's thought that changes in connectivity might provide insight into the fundamental properties of how brain networks function. However, interpreting fluctuations in connectivity is a difficult problem due to the low signal-to-noise ratio inherent in fMRI data, physiological artifacts, and variation in signal mean invariance over time. In general, it's unclear whether observed fluctuations in connectivity should be attributed to neuronal activity or simply to random noise. There also remains uncertainty regarding the appropriate analysis strategies to use and how to interpret results. In the literature so far, the sliding window correlation approach has been particularly popular. So let's illustrate that approach. Here we've extracted two time series from two regions of the brain. You see one in blue and one in red. And what we're going to do is we're going to calculate the sliding window correlation. So basically we're going to make a window of length 15. We're going to calculate the correlation within that window, and then we're going to move the window one time point over, calculate the correlation, etc., as we move through the entire range of the time series. If we do this, we get the following compelling signal, which shows how the correlation fluctuates across time. Note that the correlation fluctuates between 0.6 and negative 0.6, and it does so in a very smooth, nice manner, which seems to imply that there's something compelling going on. However, I've been a little disingenuous here because the two time series that I showed on the previous slide were actually generated to be independent of one another. Therefore, there shouldn't really be any correlation between the two time courses. Therefore, what we're seeing here is just simply random noise. So why does it look this way? Well, the fact that we're using the sliding window correlation induces a lot of autocorrelation in the signal. So we're going to get a very smoothly varying time course that looks compelling. Also, the fact that we're using a very small time window is going to give rise to a lot of variation in the signal. So it's quite natural to have signal line between 0.6 and negative 0.6. just due to random variation. This is illustrated further in the following graph, which shows the maximum correlation, so the highest correlation observed using completely null data, so completely independent data, for time series of length 150, 300, 600, and 1000, using sliding windows of length 15, 30, 60, and 120. As you can see, if we use small window sizes of length 15, it's actually not so uncommon to see maximum correlations of up to 0.9. Therefore, and this is purely on random noise, where there's really nothing going on. So therefore, one would have to take results from sliding windows of that size with a grain of salt. We see, however, if we move to window sizes of, say, 120 time points, this problem is negated, and we don't see spurious correlations that are that high. However, we do lose some ability to detect transient changes in correlation. It's been interesting to work on this area because it actually mimics discussions that happen in the finance literature in the past maybe 2 decades. So in the finance literature, both time variances and correlations between time series have been extensively studied. Here, methods such as sliding windows and exponential smoothing have been widely used. However, I think it's generally been accepted that time series models tend to give better results than sliding window type approaches. So to illustrate these models, let's kind of set up the problem here briefly. So we have two time series, y1 of t and y2 of t, so where t denotes the time point. And let's assume that y1t, y2t has mean 0 and has a conditional covariance matrix at time t given by the following, sigma t. So what we're primarily interested in is obtaining rho of t, which is the conditional correlation between the two time series, and it's given by the following equation. So in the sliding window approach, we give equal weight to all observations that lie less than w time points in the past, where w indicates the window length, 15, 30, 60, or whatnot. And it gives 0 weight to all older observations. So basically, when we're calculating the sliding windows approach, in this case where we have a mean 0, well, in the time series, well then we would just use the following formula. In the finance literature, there's been a lot of interest in modeling dynamic variance and correlations between time series. And in this case, generalized autoregressive conditional heteroscedastic Garch processes are often used. So what we can think of these Garch processes as an analog to the AR and ARMA models that are typically used to model the noise in the GLM process that we use in fMRI data analysis. So here we model the time-varying variance sigma squared of t to be dependent on the past values of sigma squared at time t minus 1, but also on the data from t minus 1. That's a univariate Garch process, and that could be used to model dynamic variances. But we're primarily interested in dynamic correlation, so we have to use a multivariate analog of Garch. And there exists many, many ways of doing this. One that's particularly popular is the so-called dynamic conditional correlations, or DCC. Basically, here are the details of DCC. What you do is you fit a Garch model to each of the time series. So let's say we have two time series, so we fit a Garch model to both of them. And then what we're doing here is we basically compute the standardized residuals for each time series. And then once we do that, we use kind of an exponentially weighted moving window to compute time-varying correlation matrices. Here we've taken null data and calculated the dynamic correlations using a sliding window of length 15. So here you see again we have a lot of variation in time. If we instead use DCC, here we see that we have pretty much a flat line which is close to 0, which is basically saying that there's no changes in connectivity over time, which is what we would like to see. Here's the analogous plot showing the maximum correlation in null data for time series of length 150, 300, 600, and 1000. And as you see, in each case we have relatively small maximum correlations, which is basically showing that the DCC isn't being tricked by this null data. So now I want to provide a brief overview of the dynamic correlation toolbox. And so in the current implementation, which is very simple, we just have sliding window code and DCC code. So we've implemented sliding window correlations and dynamic conditional correlation. And so to get a feel for how this works, let's take a look at the file example. And here, this is an example script for running this dynamic correlation toolbox. And so what we do is we generate null data at 10 different nodes, 10 different brain regions, at 128 different time points. And then we fit DCC and sliding windows to the resulting data, and then we plot the results. So let's take a look at what happens if we run this. So if we run this, it fits DCC, and then here we get the output. So this is basically just looking at what the conditional correlation matrix looks like at time 100 for DCC and the sliding windows. And so in this case what we'd expect is we want like an identity matrix here because you know, of course every node is perfectly correlated with himself, but it's not correlated with any of the other ones. And so this looks, you know, roughly like an identity matrix. Here it's a little worse. You see that there's certain kind of sporadic higher correlations at time 100. Here we see DCC, the dynamic correlation between two nodes, 1 and 3, and so you see it's quite accurately showing up as being static, while when we're looking at the sliding window correlations, it's kind of coming up as there's some sort of interesting dynamic behavior going on, which there really isn't. Okay, so this is the end of this walkthrough. I hope that you find the material interesting and that you take a look at the paper and the toolbox. Okay, see you. Bye.